So up to this point, we talked a lot about cubic equations of state and ideal gas equations of state that differ in their behavior once you get past this point, which isn't about right here. That corresponds to TR equals 1, PR equals 1, VR equals 1 on a pressure volume diagram. So we talked a lot about, once you have a temperature that's, let's say a reduced temperature that's less than 1, you're in this regime where you have these bumps. And in this regime, there's local minima and maxima. And you'll notice also that within this regime, for any given pressure, in this region where you have these bumps, you have the chance of hitting the curve 3 times. So when this happens, what solution do we work on? And so if we look at this crosses here, here, and here. Similarly, this one crosses here, here, and way out here. This is all solutions for a given pressure, and this gives you 3 distinct kind of volumes. This volume here is very small, and this volume here is very large, specific volume. So it turns out that those volumes have physical meaning. What about this volume that's here in the middle? What do we do with that? One thing that we talked about for stability is that we have to have del P, del V at constant temperature has to be less than 0 for stability. What does this mean? What does this mean? This means that if I was to increase the volume a little bit, make something a little bit bigger, let's say I go from here to here, then this means that the pressure should go down. Of course, this makes sense. If you make something that's small and if you make it bigger with the same total amount of materials in there, intuition tells you that because they're more spread out, and we're going to say the temperature is the same because each one of these lines is a different isotherm, a different constant temperature, that the pressure would likely be lower here because it's just more spread out, less constrained, and as you squeeze something down, like grabbing onto a balloon and pushing it together, it's going to have an increase in pressure. So this is for stability. So anywhere between here and here, note that this whole region, and on this other line, this isotherm, a different temperature, a colder temperature, this whole region, those 2 whole regions have a value of dP dV that is greater than 0. So think about this. If you increase the volume a little bit, what this means is that in this region, there would be an increase in pressure. But you know from experience that an increase in pressure is going to cause an increase in the vessel that's containing it if the boundaries can move, which would cause an increase in volume, and then that would feed back and cause an increase in pressure. It's not sustainable. That would be a violent explosion in this region here. Okay? So this is what there's no chance of existing in this region. It's impossible. So within a given vessel and temperature, how do you determine what pressure we should be working at? That's something that we work on next, and that has to do with the other factor here called equilibrium. So stability tells us that this whole region on both of these is not possible. It will not work. It's not sustainable. But let's zoom in, for instance, on one of those isotherms. One of those lines of constant temperature. And that happens to be in the regime where the reduced temperature is less than 1. So we have these limits now. We have this limit here and we have this limit here. This forms this basis. This is PA, and this value up here is PB. And we have, for operating in this regime, where we have a volume that's placed somewhere in this regime of impossibility, we're going to have another pressure. We'll just label this one P alpha. That is somewhere between PA and PB. So I'm going to call the intersection points of P alpha V alpha here, and then this one will be V alpha prime. So those are the 2 points on the on the pressure volume curve where the pressure, the constant pressure, which in your vessel, of course, it's going to be no pressure gradients, it's going to lead to this crossing of multiple points. And of course, this one is no good, so I'm just going to write it out so it's in your explicit notes. The pressure line P alpha on the isotherm crosses the PV curve at 3 locations. Okay. 2 are stable. 1 is unstable. V alpha prime are both attainable. It's possible to be there. But if we know we have this, maybe we have a rigid vessel and we know the volume of it, we want to calculate how much is in each different phase. If you have a pressurized canister of liquefied gas or protein, or of course, protein will be liquefied, or it'll be a solid, or it'll be a crystal. I meant to say propane. Then we have to. You can figure out how much mass is in each of the different specific volumes. So, what is the volume for this system? So we have this overall volume is going to be equal to the fractions of mass that's in each of them, or the fractions of the distribution that's contributing to these. So we're going to have WV times the density of that vapor phase plus WL times that specific volume of the liquid phase. So this would correspond, of course, with, in our diagram, V alpha, and this, of course, would be V alpha prime, because a very low volume would be very high density, and that would be liquid, and then the opposite for the vapor, which would have a very high specific volume, a very high region of occupancy for the material. So this is W. This would be vapor. This would be liquid phases of this. And so W can be mass or mole fraction in a phase for your overall system. So your system now is your material and in multiple phases, and it can be attributed either to mass or mole fraction. Properties here, of course, if it's 2 fractions for the 2 phases, the fractions of W should equal 1. Say a 50-50 mix of vapor liquid or a 25-75 mix. And so we can use this right here to get some simple rules to help our calculations. So the overall volume, the specific volume, is equal to W vapor phase, V vapor phase, as we just discussed, plus, because of this is the fact that they're fractions, 1 minus W V times V under bar L, where I simply rearranged this equation for WL and substituted it into our overall equation. So then we have the mass fraction or the mole fraction in the vapor phase is going to be equal to V under bar minus V under bar L divided by V under bar V minus V under bar L. So this is the total volume difference between the 2 points on the graph, and then this is from the center point, wherever that is, to the liquid side. So to do this, we can do one more thing, is instead of having to calculate both, we can rearrange this by a simple substitution. We can say WV over 1 minus WV is equal to V under bar L, all divided by V under bar V minus V under bar. And all you have to do is look at the graph to figure out how relatively large the distances are for those two quantities. So you go back to our graph here. Let's suppose our V is here. We'd be talking about measuring this distance here, measuring this distance here, and that's all you need to know to calculate the fractional distribution of your material in the two phases. I like to learn from graphs a lot more than trying to just plug through numbers. It's very conceptual to look at graphs. So what this is called is simply the lever rule, because you're making a lever out of the graph that's balanced on this V in the middle. So this is the lever rule, and you can actually apply it to all other kinds of variables. So that's the basics of that. I still haven't told you about equilibrium, but equilibrium needs to stand alone in its own video because it's a little bit more involved. Conceptually, it's pretty straightforward. Calculating it becomes a little bit more challenging, but not terribly bad. So stay tuned.